not, unfortunately, not very usual for HRI to manage to have interface with the schools in the neighborhood. Being a somewhat small institution, it's rather difficult. But once a year at least, we have the tradition of organizing this talent test, in which we are very happy to see that schools participate very enthusiastically. This year, I must apologize for being a little sloppy about this whole thing, in the sense that there were some problems regarding venue, and then when the venue could finally be fixed, the dates unfortunately clashed with some other national exams, and therefore a few schools could not participate. For that, we are indeed very sorry. From this year onwards, we will use the school next door as the venue, and so there will not be any problem, and we'll be able to go ahead and plan in advance, and I do hope that all the schools will be able to participate. But for those schools which did participate in spite of the difficulties that we put you through, I'm particularly grateful to them, and I'm very happy that you have turned up today for this prize distribution function. There is a general desire for students who are opting for science to know about the why, let's say, the universe, its beginnings, and so on and so forth. And there is certainly a certain amount of romanticism about it. And if the beginning is to be understood, then certain difficulties have to be overcome, and to overcome them, we need something called the string theory. And so we thought that introduction to string theory would be a very good way of broadening your horizon. And fortunately, we have a very strong string theory group, and one of the very prominent members of that string group is Professor Rajesh Gopakumar. Rajesh did his undergraduate work in IIT Kanpur, was then in Princeton, where he got his PhD, and then a postdoc at Harvard, and came here in the early 2000s. So he has received almost every prestigious award in the country that you can think of. He also has the ICTP prize, and that is not really introduction. The real introduction would be through his lecture that you will be hearing now. So without any further introduction, it's Rajesh Gopakumar to talk about string theory.
So I'm really delighted to be here to be speaking to so many of you, especially the bright youngsters of the talent search. Perhaps Jantada built up my expectations a bit too much that I would explain string theory. I'm not sure I'll be able to do that in the course of a short short lecture, but hopefully what I will do is to make you appreciate some of the questions it asks that string theory tries to ask, and more importantly, how it fits into the broader context of our understanding of the physical world, of the universe. So that's I define my task in that way so as to sort of keep it a little reasonable, and I hope you will get that sense. Towards the latter half, it might become a little bit more technical and a little bit more in detail, but please ask me either during or after the talk. But before I embark on that sort of lecture, since this is for the young audience, I just wanted to dwell a little on this word quest over there, which is very akin to the word question. So just for the young people, since you clearly have a talent for science, I just wanted to say that science is a quest of mankind, and in some sense one of its nobler ones, and perhaps one of the most noble ones. And for a scientist, this his or her quest gives a certain meaning to life in a sense, and the thrill of discovery or understanding, even if it's very humble or personal in a small way, that is what enables the scientist to sort of transcend the day-to-day, the mundane, and it makes life worthwhile. So I just wanted to tell you that perspective from a scientist's point of view. I don't want to over-romanticize it, the life of a scientist, as many of you, the students and others in the audience know. It also has its share of ups and downs, and its drudgery and pettinesses and everything, but in some ways, the sense of the quest, I think, makes up for a lot of it, because it sort of anchors you to a sort of a deeper level, something much deeper and long-lasting, and you have the sense of participating in howsoever humble way in one of humanity's great glories. So that's, I feel, something you should keep in mind. I know parents are often worried, oh, beta science leke fir kya karega, BTech, MBBS kar lo, IAS, MBA kar lo, fir life bilkul set ho jayega. So this thing, but even my parents felt that way, and I think it is the job of parents to worry, because that's what they do. Now I'm a parent, no. But if you sort of sense within you a certain fire, if you have a certain a passion for science or mathematics, I think you should just follow it, and you will not regret it, I think. So you may not end up with $1 million house in San Francisco or a Lal Batti Gadi to escort you or whatever, but I think those things will all pale once the novelty wears off. I mean, discovering a theorem or a law of nature is something for all time. So just keep that in mind. So anyway, enough of Gyan. I'll sort of try to embark on this, give you an idea of a particular quest. Even within string theory, it's a very specific one, and if the title is a little mystifying, I'll try to shed some light on it. So the way I've sort of tried to frame it is as sort of like, if you wish, a set of snapshots from a trek. So supposing your friends have gone for a trek in the Himalayas, and they come back and they show you all these very beautiful pictures of the white vistas and the snowy peaks and everything. So it will be a bit like that, unfortunately, because so that it's not the same as actually being there and experiencing the thin air and the grandeur of the scenery. But hopefully the snapshots will convey to you a sense of what it is. And so let me just continue with that metaphor a little, of the Himalayan metaphor. So this is Kanchenjunga. As you know, it's the highest peak in the eastern Himalayas, the third highest peak in the world. And this is a picture of K2, which is on the northwestern corner of the Himalayas. So one thing which, if you think about it, you will realize that these two are, of course, very high peaks. They are locally the maxima, if you wish. But it wasn't always known. I mean, clearly in the past it would never have been known that they are part of one connected mountain range, right? I mean, someone living in Sikkim, they see a lot of mountains, they see this thing there. They would never have been able to guess, unless they had traveled or whatever, that there is a connected one range that takes them all the way several thousands of kilometers to K2. So this is something which had to be sort of mapped out, if you wish. People, explorers went and then they traveled from one end to the other, and slowly you built a picture, and you sort of built a picture of a map of the Himalayas, going from the Kanchenjunga somewhere here to K2 somewhere there, and of course there was Everest in the middle. So this is something which had people gradually mapped out. But of course nowadays we have marvelous technology, and we can literally see it. You just open Google Earth or something and you can see the whole Himalayas all at one glance. You get the whole panorama, at least from a satellite picture. You can see it all. So what I would like to sort of point out is that our understanding in physics has also come in much the same way. So you first you sort of do a sort of detailed ground survey in a small area. You try to discover some simple laws that describe a few things. So if I drop this, or I see that, or if I throw this, it follows a certain parabola. I throw a ping pong ball, that also follows more or less the parabola. And then various things, and I notice similarities. I try to infer a simple law describing the motion of things that I throw. And similarly, someone else studies the motion of fluids and discovers simple laws of the behavior of fluids. So in physics, our understanding has come that way. And then with these simple laws, you try to piece together into a larger picture to get more general laws, which cover even more and more phenomena, which can sort of encompass even larger things. And when you broaden the scope that you see the connectedness of the various peaks. So you might locally, someone has discovered the laws of electromagnetism, and that's really a high point in science, describes so much of our electromagnetic phenomena, which governs, which allows you to hear me through this microphone and see this on the screen, etc. So there are local peaks like that, and similarly I will describe about the force of gravity. That's another peak in our understanding. So there are several of these, but as you broaden the scope, you see the connectedness of these, and then some kind of a Himalayan range. So this is the sort of thing that this is the way in which our understanding of physics has grown. But let me first emphasize a few basic things about the laws of physics. So as I said, they embody our ability to discern certain regularities, to spot certain patterns amidst very complex behavior. So of course life is complex all around us. You go into the streets of Allahabad, there are cycle rickshaws coming from there, and there are trucks coming from the other side, and you are lucky to be able to cross the road. But amidst all this complex behavior, there are patterns that people have spotted, and that's like I said, if you throw things, it is in the streets of Allahabad or elsewhere, they follow a certain regular pattern. So people have spotted these patterns, and that's how the laws of physics have been developed. And it's certainly remarkable. One of the remarkable things about it is that it's capturable in mathematical language, in very precise mathematical language. There is an equation that describes the sort of the curve or the trajectory that an object that you throw follows, namely a parabola, as probably many of you know from your high school physics. There's a precise mathematical description which is available, which in fact the remarkable thing is that even as we widen the scope of these laws, we describe not just things falling over here, but we describe even the rockets that we send out into space. We are able to keep describing them in precise mathematical language, even as we widen the scope of the laws to the very small, to the very large, to sort of longer periods of time, etc. And we'll describe that. But one thing to keep in mind is that as you keep broadening the scope, the precise mathematical language that you use sometimes requires, the mathematics becomes more sophisticated, more unfamiliar, and sometimes needs to be developed. But also conceptually, it becomes sometimes more, it becomes richer in some ways, but also sometimes more abstract. I will give instances of this as we go on. So these are sort of just general remarks to keep in mind about the laws of physics. So I mentioned about this Himalayan, this thing, in some sense there are sort of two peaks in 20th century physics, and especially 20th century theoretical physics has stood on two pillars, or there are two sort of high points in the evolution of theory, and these are what is called general relativity, which I will describe. It's a theory of gravity. You might have heard this is what Einstein is famous for, and this year is in fact the 100th year when Einstein wrote down his equations, as I will describe, which describe gravity. So this is the 100th centenary year for general relativity. So from 1915 that this was. So this is one of the peaks, and the other is something which is maybe even less familiar. You may not have heard the term. It's called quantum field theory. It is basically, you might have heard the term quantum mechanics. It is in some ways the elaboration or completion of quantum mechanics, and that's what these are the two major frameworks on which most of 20th century physics has stood. And they are very successful. Both of them are very successful in their own ways. For instance, GTR as a general theory of relativity, that's why the T is there. So general relativity has given us a very successful theory of the whole universe, the cosmos as a whole, and its evolution on the very longest time scales. So from very early, from the history of the universe to the present day, there's a very successful theory based on the equations that Einstein wrote, this framework of general relativity is very successful in describing very large scales. So the biggest that we can explore with our telescopes and other things. Whereas quantum field theory has captured the physics at the atomic scale and beyond, below. So everything from the atomic scale and the collections of atoms, so even the behaviors of metals and semiconductors and all these things, starting from there to the very smallest length scales, which are 10 orders of magnitude smaller, so to say, which are as small compared to the atomic scale as the atomic scale is compared to us. To that smallest length scales, these are probed in the accelerators that you would have heard about in CERN, in Geneva, etc. So quantum field theory has sort of captured that very accurately in very precise mathematical language. So these are two great successes of physics that you can be justifiably proud of. In a sense, hinges on our modern understanding of one force, which is of gravity. So this is what I will concentrate on. So gravity, as you know, is the most ubiquitous force in nature. It is the most common force. Every child feels it. Every child who's from a few months old tries to stand up and falls down knows that there is a force of gravity. So it's something we can immediately feel in our bones, so to say. So this force, of course, has been known for a long time, but it was not until Isaac Newton, who lived in the 17th century, that one realized that there was a universal law which described gravity throughout the cosmos, at least the cosmos as far as Newton knew it at that time. and this Newton's law of gravitation was, in that sense, much broader in scope than the laws which told you that things fall on Earth with an acceleration which is approximately 9.8 meters per second square. This is a more general law which encompasses many more things, and this is something, again, probably you have seen in school. It is the famous inverse square law that the force between two objects is directly proportional to their masses, m1 and m2, and inversely proportional to the separation of the two. It is in the direction along this thing. And well, this is really the vector pointing inwards, so it's an attractive force. And so this force is a vector, and there's a constant which measures, a universal constant called the Newton's constant. And this is a universal law in the sense that this is supposed to describe not just the bodies on Earth, but also the bodies in the solar system. And at that time, of course, one knew only up to the solar system, but comets and planets and asteroids, all these things are described by Newton's laws, and in fact that's what you mostly use. Even Mangalyaan was sent to Mars based on calculations using Newton's laws, because for most purposes that's good enough, even though now we know that it has been actually supplanted. So what was not realized at the time of Newton when he proposed this law, so he proposed it as a universal law, but what was not realized, and this is often the case in physics, that this law has a certain validity. It is valid for a certain, it's valid in a certain range, for certain phenomena. I will just describe that in a moment. But it is like any say, ticket that you get to for travel. It is valid for a certain period or for a certain. It's not valid necessarily all the time, but it's important to know when it is valid. Otherwise, you may misuse it, or you might be found traveling without tickets. So it's important to understand the range of validity of a law. And so what was not realized in Newton's time, but which we now understand, is that this law is true. It's true in the solar system almost to very high accuracy, except in the orbit of Mercury there are corrections which are observable, but other corrections are not things you can observe. But nevertheless, there are places in the universe where this law breaks down, and it breaks down under two different sets of fairly extreme circumstances, extreme from the point of view of our experience. And what are these circumstances? So this is the the limitations. So I want to describe to you the limitations of Newton's law. So Newton's law is very successful, but when you try to apply it to objects that move very fast or spin very fast, for instance, this is a sort of an artist's impression of what's called a pulsar, which is a star which is rotating very fast. It's a very compact star, and it sort of sends out a beam of light due to its magnetic field, charged particles moving in a field. But anyhow, it's an object that people have observed. Astronomers have observed and studied very well, and it is known that Newton's laws don't apply when objects move very fast. They also don't apply. This is the right-hand side. Is a picture of a galaxy, and at the center of the galaxy, typically the densities are very high, and it is believed that there are what are called supermassive black holes, which I will come to. When the density is very high, once again Newton's laws is not valid. So just remember, when does Newton's law break down? It breaks down when things move very, very fast. So very fast means very close to the speed of light. So those who know about the speed of light can appreciate what very fast means. And very dense, so typically much more dense than the sun, for instance. So when that happens, again Newton's laws, as you can see that there are substantial deviations from Newton's laws. Newton's laws are not adequate to describe these two different sets of circumstances. So that's very interesting, because one has found a law which Newton's law is very successful in its regime of validity, but breaks down. And what Einstein succeeded 100 years ago is he succeeded at least partially, and we'll come to this partially, that's a very important partially, but he partially overcame these limitations. And what he described, his description of gravity, which I will just mention, is something which is applicable at very high velocities. So it's very good at describing these pulsars, for instance, and some of the best tests of Einstein's theory are from studying these pulsars. So his description of gravity overcame that limitation of Newton's laws. It also works fairly well for moderately high densities, densities which are higher than those of the sun, for instance, densities of things like neutron stars. It works for those and gives successful description of those, a lot of the study of astrophysics is based on our modern understanding of the nature of stars. Using Einstein's theory, and so he overcame the limitations at least partially because he could overcome the first one about the velocities, and he could do this for moderately high densities. We'll come to why this partially comes. It's related to the fact that I have put in a qualifier here that it's only for moderately high densities that Einstein's laws work. But the important point I would like to get across to you is that he managed to overcome these limitations in Newton's laws not just by changing Newton's laws a little. I showed you that Newton's laws, the equation over there. You might think that, oh, okay, it breaks down for small velocities, so I have to add some term with some velocities, or I have to make some small correction for some when the density is more. So that is not how Einstein overcame the limitations of Newton's laws. And in fact, it's a very good lesson in how physics continues to surprise us, that his framework or his description of the force of gravity completely changed, was completely different. It on first sight looks nothing like the Newtonian framework. So what he did was he tied up the description of gravity with the geometry of space and time. So not just space, of both space and time together, he realized has a geometrical behavior which is different from the ordinary ones which we are most used to, in which the sum of the angles of a triangle is 180 degrees. You can have, for instance, geometries which are more like the surface of a sphere or a curved surface. So when you draw, like on a sphere, if you try to draw a spherical triangle, the sum of the angles is greater than 180 degrees. So you can have very different kinds of geometries, and what Einstein said was that the space and time have a geometry which is very different from which can be very different from what we are naively used to thinking. And moreover, the space-time is not just some kind of a passive stage for all the events that take place. We think of space-time as like a stage on which we move, and the cycle rickshaws are moving, and the trucks are moving, and everything is moving on a fixed space and time. But that's not how you view the geometry of space and time in Einstein's description of gravity, because space-time becomes a participant in the whole drama of physical events, because it captures the force of gravity. And so depending on how there are objects, whether there are heavy objects here or no objects there, the space changes accordingly, or the space sort of modifies itself to in a very precise way to capture that. there's a sort of a picture that you can give of this, which is sometimes it's somewhat misleading, but it's probably something to just keep in mind of a massive object sort of curves the space. It's not just the space, it should be space and time, but you can't visualize that, so this is just a crude caricature of that curve. So, like the Earth sort of curves the space-time around it in such a way that a satellite which is moving around the Earth feels that curvature and therefore moves in a sort of a curved orbit, in an elliptical orbit. So he tied up the geometry to the presence of massive objects. So the mass and energy which is there in the universe tends to change the geometry in a very precise way. And so it's in a very different mathematical framework from Newton's laws, which were based on just some force between two objects. Whereas here, what Einstein proposed was that there is a quantity which is called the metric, which is a measure of distance on a space-time, distance and curvature, how much so for any surface, even for a two-dimensional surface, you can describe, you can give a sort of a metric which measures what is the distance from point A to point B, and how much, and if you know how, so that metric is sort of a modification of our usual sum of the squares Euclidean distance that we are familiar with. So this depends on space and time, this metric, and it measures the distance and curvature. Einstein wrote down a set of equations in the picture of Einstein that I showed a couple of slides ago. He had written the Einstein equations, which are equations that determine this metric in terms of which determine this metric in terms of the matter and the energy that is present. But the remarkable feature is that this description, which at first sight looks nothing like Newton's law, reduces to Newton's law in the limit of low densities and velocities. Yes. So when the velocities are very small and when densities are low, then this whole mathematical framework of Einstein's equations remarkably reduces to the Newton's equations. So it's quite a remarkable fact that this geometrical description is behind Newton's laws, and Newton's laws is only a particular limit of that description. And as I said, this picture of gravity in terms of the geometry of space and time is a very successful description, all the way to the very largest scales that we have probed, which is about 1 million times the size of the Milky Way. So the Milky Way is just a small spot. There are maps like this that astronomers now have of the full universe, and we've mapped the universe to distances about 1 million times the size of the Milky Way galaxy, and the Einstein's equations give a very successful description all the way to these scales. But that is not the full story. So like I said, all physical laws, it's important to understand what is the regime of their validity. When does your sort of ticket expire? So that for gravity, you know that this picture of Einstein's can't be the full picture, because ultimately the physical reality is based on what is called quantum mechanics, and we know this from the existence of atoms. Atoms wouldn't exist without in a classical world. So it's the framework of quantum mechanics that describes atoms, and so we know at some very deep scale, at some very small distances, the physical reality has to be captured in a quantum mechanical sense, at least that is our understanding so far. And the difference in a way, in one line between classical mechanics and quantum mechanics is that what we think of as classical observables have only statistical outcomes when you're at the quantum level. You can measure an expectation value, or so you get an average expectation value of a classical observable, like a position or a velocity, but that makes it very difficult to think of gravity in a quantum mechanical way, because then how do you think of space and time quantum mechanically? How do you think that space-time might be emerge as a statistical average of something? That is very difficult to sort of conceive, and this has been the sort of the puzzle, and that explains the title of my talk about the quantum space-time. So what do you mean by space-time? You can, with great difficulty and with some mathematical sophistication, you can understand the geometry of space and time, Einstein's framework. But this, having understood that geometry, which is some generalization, as I said, of spherical geometry, that geometry, how do you think of that as coming from some kind of statistical average, as some coarse-grained or some sort of averaged out quantity? Because we think of space-time as something very, we think we know what is space, we think we know what is time, but how can it be some kind of an averaged notion? And more technically, you ask of what do you mean by quantum fluctuations of the metric. So the basic question is, how do you reconcile this Einstein's picture of geometry of space and time with quantum mechanics? So that's sort of the basic question, and this is where I have to come to the limitations of Einstein's law, because as I described, Einstein only partially overcame the limitations of Newton, and you see that there are regimes. As you enlarge the scope of Einstein, you try to, just like Newton's laws broke down when people tried to apply it to more and more dense objects or more and more fast spinning objects, as you try to apply Einstein's theory to even larger domains, then you realize that even that breaks down, and in some sense, again, it happens under two sets of limiting circumstances. It happens at very short distances, what is called Planckian distances, which is a very small length scale, much, much smaller than what we have probed. So at these very short distances, try to describe things with very high densities or at very short distances, you inevitably run into these breakdown of the Einstein equations. So Einstein's equations also have a limitation. They are not the complete description. And in fact, physics always progresses by increasing your range, and you never know when you have, there probably is no complete description, but you can make successive approximations. And we have arrived now at a limitation of Einstein's laws. But you might take the attitude, well, who cares about quantum gravity or the gravity in a quantum way? I mean, it seems so removed from anything. So why should you bother about a theory that overcomes all these limitations of Einstein's theory? Why should you bother about a quantum theory of gravity? But there are actually, again, two fairly compelling reasons for which we need quantum gravity. We need it to investigate the birth of the universe. So as I said, we can describe the universe. This is a sort of a picture, a cartoon of the evolution of the universe. This horizontal axis is the time axis, and the universe has been expanding, and we understand the evolution of the universe, the various phases in the evolution of the universe, almost till the tip over there, the so-called Big Bang, and it's only very near that tip, that means a very, very small fraction of a second close to the Big Bang, that Einstein's equations break down, and we know that we can't push our understanding all the way till the end. So we have a very good description, but it breaks down at some point. So if you want to sort of understand what is going on, and in fact now with the cosmological experiments, we are able to probe the physics very near that Big Bang, we need to understand what a quantum theory of gravity is. So that's one place where we need to understand it. The other is what are called black holes, which maybe again in the popular literature you might have come across. They are, I will talk more about them later, but basically they are formed when a star collapses, when it's super dense and the gravitational force is stronger than any other force, any other pressure that can keep it steady. It collapses into a sort of a super dense point, like a point-like object from which even light doesn't escape, and that's why it's called a black hole. This is a picture of a black hole-like object which is pulling out gas from its companion star, a regular sun-like star. So it's these objects again are there are by now several candidates of black holes that astronomers have identified in the sky in our galaxy, and perhaps, as I said, even in the center of galaxies there are believed to be what are called supermassive black holes, which are a mass about 10,000 times that of the sun. So now I will go into something a little bit more technical. So now I'll try to come to how string theory tries to sort of overcome some of the limitations of Einstein's laws, and what that journey is taking us towards, and it is something that is still not complete. But first, let me tell you a little bit about how people historically try to address this. In fact, there's a superficially analogous situation in the study of electrodynamics. So electrodynamics, as you know, is what describes the electric and magnetic forces. You know how motors work, how induction coils work, and that's why you have all the wonders of electricity. That's a very good classical description. It is what Maxwell wrote down equations which describe that. These are like Einstein's equations, much simpler, but they describe the electric field, the magnetic field. The electric field, magnetic field are sort of the things that encapsulate the electrical forces and the magnetic forces. Maxwell's laws give a good classical description. There are a set of equations, but we know again they break down. They break down at the atomic scale. In fact, that's why people realized they were first puzzled at the existence of atoms in which you have an electron moving around a proton. Maxwell's laws would say that cannot happen. That would not be a stable object. The electron would spiral into it. But there's another place where Maxwell's laws also break down. That's when the electric fields or magnetic fields become very strong. So it's again a bit like Einstein's theory that very short distances or very strong values of the field, the equations break down. But there is a very successful quantum theory of electrodynamics, which was developed by people like Richard Feynman, maybe whose name you might have heard, and others. So it's a very successful theory, one of our most successful theories of the physical world. And you might hope that, I should have said, this theory is in the framework of what is called quantum field theory. So there's a very general procedure for any field theory. So we started with electric field and magnetic fields. These were classical fields. How do you treat them at the quantum level? That is what the framework of quantum field theory tells you. And there is a well-defined framework by which we understand the fields of electrodynamics at the quantum level. And you might hope to address the problem of, so to say, quantizing the gravitational field in a similar way. How the gravity is also a field. I told you there is the metric, which is the object that determines the distances and curvatures. That you can view as a field because it varies from point to point in a general curved geometry of space-time. So this gravitational field, G mu nu, it's a generalization at first sight, a sort of a small generalization of the electromagnetic field. So you might think that can be treated in a similar way, but in fact that's where you face the limitations of quantum field theory, because all attempts so far of trying to describe the force of gravity through this framework, which is very successful for electrodynamics, is not successful for gravitational field for reasons that I cannot go into now. But but at a very qualitative level, it is presumably because the gravitational field is very different from the other fields. It is describing the whole geometry of space-time itself. The normal framework of quantum field theory assumes that there is some space-time, and then there are other fields like electric field or magnetic field which are sitting on that space-time. But it's like, as I said, there is a stage and there are characters on the stage. As far as electrodynamics go, the electric field, the magnetic field, and all are characters which are moving on a fixed stage. But in the case of gravity, the stage of space-time, the stage itself is sort of moving, and then the framework of quantum field theory seems unable to address that, to tackle that. So quantizing geometry is even more subtle than quantizing any of the other fields. And this is where, in some sense, string theory enters. I would say it is some kind of a conservatively radical modification of quantum field theory, because it is in some ways radical. It sort of generalizes the idea of a point particle to some extended objects which are string-like, which are extended, and then you try to understand the quantum dynamics of these string-like objects. By the way, string-like objects appear in many areas of nature. They appear in superconductors, they appear in the strong interactions. So that these are, and in some sense, they are related to Faraday's picture of electric and magnetic flux tubes. But anyhow, if you try to understand the dynamics of these extended objects and not point-like particle objects, that's where string theory arose. It is conservative in the sense that it does not modify quantum mechanics. It sort of takes over many of those features of quantum field theory, but it generalizes the idea of the point particle in this way. But it's a very highly constrained framework, because if you try to consistently describe the interactions of these extended objects, there are many consistency requirements, and it's much more constrained than a quantum field theory is. And in fact, that was the reason people became initially very excited by this, because it addressed some of the difficulties that quantum field theory had with respect to gravity, namely in understanding how the quanta of the gravitational fields scatter with each other, etc. But for many years, the whole problem of what is a quantum space-time was not quite addressed, and this was a more challenging question. So certainly it showed a lot of promise. String theory showed a lot of promise in addressing some of the problems that quantum field theory had, but the conceptual picture of what is quantum space-time was not something that one made very much progress with. But this changed about 15 years ago when an Argentinian physicist called Maldacena, he used the string theory to come up with a proposal for how space-times, a large class of space-times, behave at the quantum level. And the class of spacetimes that he studied can be sort of viewed roughly like this. This is a picture, I don't know whether you have seen. If you like art, you might have heard of the artist called Escher. He painted these sort of very interesting drawings. You can look on Google Images and you will find many of his interesting, they are very creative pictures, very geometric, and in some ways captures a lot of deep mathematical ideas. So this is a picture of his which is called the Angels and Demons. So if you see there's a demon here, and if you look at the white, there's an angel. But the geometry of it is what is called the geometry of hyperbolic space. It is a space of constant negative curvature. So unlike a sphere which is positively curved, a hyperbola, as you know, which is like that, has a negative curvature, and this is another representation of the hyperboloid in a less familiar way, in which all these have the same area, though they look smaller and smaller. The space-time is curved in such a way that each of these angels and demons have the same area. So it's a negatively curved space, and physicists, of course, don't just want space, you want space-time, so there's a time direction as well, which is along, if you wish, the vertical axis, so this is more to be thought of as some kind of a solid cylinder. So this is a large class of space-times. These are called anti-de Sitter space-times, and what was proposed is a description of the quantum, what is the meaning of the quantum space, of these class of quantum space-times. This is, of course, a classical picture. What does it mean to describe this what he proposed was that these are described by a quantum field theory, but unlike, the surprise was it was not a quantum field theory of the metric or anything like that. It was a very different quantum field theory which in fact lived in a different space altogether, space-time altogether. In fact, in this particular cases, it lives on the boundary of this cylinder. So if you view this as a solid cylinder, the surface of that cylinder, which is a two-dimensional surface, is a one lower dimension than the solid cylinder, which is three-dimensional. And the quantum field theory, in this case, would live on this. The quantum space-time is described in terms of a quantum field theory, not of the metric, but of a set of fields which live in the in one lower dimension, and the fields are very much like those in electrodynamics. So anyway, the fields on this boundary are very much like in electrodynamics, but the picture that comes across is that the quantum gravity is in some sense holographic. You have probably seen these holograms, which are sort of two-dimensional objects which which look three-dimensional. So this is something like that. There is a two-dimensional, or maybe for our 3 plus 1 dimensional space-time, there's a 2 plus 1 dimensional boundary which captures the behavior of the quantum space-time in the interior. Another way to say it is that, very roughly, imagine as if the whole information about the quantum space-time inside this room is captured by the behavior on the boundary, namely the walls and ceilings of this room. So it's a bit like that. It's a bit counterintuitive that everything is captured in a sense in just the boundary, but that's one of the remarkable consequences of this. So this may seem very esoteric, very sort of removed, but actually it sheds light on some very important puzzles, and for this I have to take you back to these objects called black holes. which, as I said then, were formed from the intense gravitational pull of a dying star, and the Indian physicist Subrahmanyam Chandrasekhar was one of the first to sort of predict their existence, that eventually a massive enough star cannot resist its own gravitational pull, and it will collapse to this kind of a super dense point, if you wish. And there is a solution of Einstein's equations that describes these kind of objects. It has very interesting properties, and but it also has these so-called singularities, or these places where the equations break down. So you can trust the equations all the way to a certain point, but then they break down. So so you have these solutions of these black holes, and there seem to be objects in the sky which correspond to them. But there are many puzzles associated with these black holes. In fact, they have become quite a remarkable theoretical laboratory, at least so far theoretical, for studying quantum effects in gravity. Because, and in fact, Stephen Hawking, of whom maybe many of you have heard, and made one of the most remarkable discoveries in this. What he discovered was that if you have a black hole and you want to describe it not by just Einstein's equations, but if you describe it with quantum mechanics, that whatever be the quantum mechanics, we still may not understand what the quantum mechanics is, but what he was able to show was that for a sufficiently large black hole, the quantum mechanical description will necessarily have to assign black holes a temperature and what is called entropy, which maybe you're not that familiar, but it is one of the thermodynamic concepts that are associated with temperature. So you know, temperature is something that you associate with a large macroscopic object. You associate a temperature with which has a lot of structure. So Hawking suggested that you should assign a temperature which is inversely proportional to the mass of the black hole, as well as this constant g that appeared in Newton's equation. Remember the universal constant of gravitation, and something called h bar, which is essentially what is called Planck's constant. Those of you who are in 11 and 12 at least have probably heard of this thing called Planck's constant, which is a measure of the quantum nature of the object. And there's a universal temperature of this kind and a similar entropy. And these, when an object has a temperature and an entropy, that's suggestive of an internal structure, just like meaning that there are it is comprised of many degrees of freedom. Otherwise, the notion of a temperature or of entropy or any other thermodynamical quantity doesn't make any sense. You don't assign a temperature to a single electron or a temperature to a single proton. You assign it to a collection of these, a large gas, an Avogadro number, 10 to the 23 of them, typically. So for a black hole, to assign a temperature, to say that a black hole has a temperature, suggests that a black hole should have some internal structure. It should be built of some kind of deeper set of atoms or some internal constituents. And this conflicts with the Einstein's picture that you get from his equations, which have a unique solution, as I said, a unique solution for a given black hole. And so this discovery of Hawking was very important to suggest that there is more to really describe black holes. You have to understand them in a quantum mechanical way, and that suggests how to go beyond the Einstein's equations. And this picture that I described to you about this holography, in fact, captures the physics of the black holes, at least in this class of anti-de Sitter spacetimes, where you can also have black holes, and you understand that. You can understand its temperature and its entropy and other things in terms of this boundary description. So it's as if there is a description on the boundary of this anti-de Sitter spacetime, which is at a finite temperature, which that captures the behavior, the quantum mechanical behavior of the black hole, and that temperature of this quantum field theory is the Hawking temperature of the black hole. And one obtains a description of the so-called microstates, or the internal constituents of the Bekenstein-Hawking entropy. This kind of entropy, which is a measure. Entropy is a measure of the number of configurations that an object with internal structure can have, and this entropy is precisely reproduced from this holographic picture that arises from string theory. So that was to just give you an idea of the kind of questions and how string theory addresses some of them. So let's come back to our original quest and ask, what have we learned? Well, in some sense, it is an ongoing quest. We have learned, because it's only in a class of spacetimes, this anti-de-Sitter class of spacetimes, even though that's a very large class. But in those cases, we now have a reasonably confident description of what the quantum spacetime is. It's probably holographic in nature, and what gives us confidence is in its ability to understand things like this Bekenstein-Hawking entropy in a microscopic way. And a bigger picture that emerges. Remember, there was this puzzle about how can space and time come out as some kind of statistical notions. And from this quantum field theory, the space and time in the anti-de-Sitter seems to emerge in some very mysterious way, which we still don't completely understand. And it's a bit like how you, from the discrete atoms, which we don't see with our naked eye, we still have continuous objects like the air in this room, or the water that is in the glass there. So all these seem to emerge they look very different from the underlying atoms. In some ways, space and time seem to emerge as continuous objects. We see space as a continuous thing. We can go continuously from here to there, and in time we seem to move continuously. But perhaps these are approximations, and that's the quantum space-time is perhaps more subtle and has a discreteness to it, just like atoms are an underlying discrete entity underlying the familiar water or fluids around us. So that's perhaps one of the lessons. But we need to understand this better. In some sense, we need to decode the hologram better in these particular cases, and to ask whether is this how quantum spacetime behaves for all classes of spacetime, not just for anti-de-Sitter, these sort of negatively curved spacetimes. So let me just say that in the meanwhile, this is sort of a tangential comment, that this connection has also uncovered a lot of new facts about quantum field theories, which describe many of the other forces of nature. When quantum field theories are interacting very strongly, this connection between quantum field theories and gravity has shed new light, not just on gravity, but also on quantum field theories. In some sense, it's the next best thing to having experimental evidence, because it makes predictions. This connection makes predictions about things which were there before string theory, namely quantum field theory and general relativity. These are about 100 years old, these subjects. And so it makes non-trivial falsifiable statements, and which have in fact been validated. So that's showing that the theory is able to make new non-trivial statements, and so we should trust the picture it is giving. This gives us confidence that we should trust the picture it's giving about quantum space-time. But in any case, the mechanism for this connection between gravity and quantum field theories, which is one of the things that most of the string theorists are currently trying to understand, I think this is potentially powerful in many other applications, because quantum field theories arise in many other situations in nature, as I said, starting from metals and superconductors and semiconductors and so on. So this is a very potentially very powerful connection, and I think these two peaks of 20th century physics will be sort of linked in the 21st century into a sort of this Himalayan panorama that we started this lecture with. So before I leave you all especially the younger people in the audience, I just wanted to share with you some extraordinary statement by one of the very famous, probably one of the most famous mathematicians of the 20th century, the second half of the 20th century at least, called Contd. So let me just read it out for you. It says, in our acquisition of knowledge of the universe, whether mathematical or otherwise, that which renovates the quest is nothing more or less than innocence. It alone with humility can unite humility with boldness so as to allow us to penetrate to the heart of things. This unique power is in no way the privilege given to exceptional talents. In fact, it is not these gifts, these exceptional talents, that enable one to surmount the invisible yet formidable boundaries that encircle our universe. It's only innocence that can surmount them. It's a very deep statement about the innocence and the wonder, which is what enables you to surmount the invisible and formidable boundaries. So I hope with your innocence as youngsters, you will sort of participate in the quest. So hope to see you on the trek sometime.
I'm sure Rajesh would be willing to answer any questions that you have. So, anything that you want.
Sir, I wanted to understand why the laws of gravitation fail at higher density locations.
The Einstein's laws?
No,
or
sir, Newtonian laws.
Newtonian laws. It's not obvious from, if you just look at the Newton's equations, nothing in it tells you that it should fail. It's only an experimental discovery, if you wish, that they ultimately fail. Theoretically, you realize that Newton's laws are inadequate. It was realized after the discovery of what is known as special relativity, which Einstein discovered in 1905, is something that all physical laws must obey. Namely, they should be sort of objects, any observer which is moving at a uniform velocity with respect to another, they should describe the laws of physics in a very similar way. And that's this requirement of special relativity, and Newton's law of gravity is in conflict with that. So that already tells you that theoretically Newton's law is not complete. It is in conflict with Einstein's special relativity, and this is what made Einstein write down a set of try to describe gravity in a way which would be compatible with his earlier theory of special relativity, and he came up theoretically with these Einstein equations, and which describe things even when things are moving fast. And so that's why experimentally then it has been observed that indeed if you look at these pulsars which are rotating very fast, their behavior is described accurately only by Einstein's equations. If you look at, and then in fact historically the earlier test was that even an object like the sun, even though it's not super dense, it also changes the geometry of space-time around it slightly. It changes it slightly enough that the orbit of Mercury is not exactly what is predicted by Newton's equations. There is a small correction to it. The orbit sort of keeps precessing, or the axis of the point at which it comes farthest from the sun or closest to the sun, that rotates a little bit by 43 arc seconds. It rotates by actually 500 or so arc seconds per century, but of that 43 arc seconds cannot be accounted for by anything else other than the Einsteinian description in terms of the geometry of space-time. So you could see that Newton's laws are breaking down, and this, of course, now that was the sun, but by now people have studied much more dense objects and the orbits around them, and you know that there are substantial corrections to Newton's laws. So experimentally, this is verified, and theoretically, as I said, it's because Newton's laws as such are not compatible with special relativity.
Thanks.
So my question is related to gravitation and the launching of satellites. So I wanted to know that do we consider the angle with which the satellite is launched from the surface of the Earth?
Sorry, what was the first part? The gravitational?
And the launching of the satellites.
The angle of launching
yes.
of satellites? Okay, of rockets which launch satellites.
Does that have any significance? Because till now we have been learning about, mass and other factors which determine the launching. So does angle have any significance?
So of course when you try to launch, it is most advantageous to launch it vertically because you want to give a certain velocity to the rockets to reach a certain height and make the satellites orbit at a certain height. So given that you have a finite amount of fuel that you can carry on the rocket, it is much more efficient to launch it vertically. So the angle is usually just 90 degrees. But for all these calculations to launch satellites and so on, unless you're doing something to very high precision, it's enough to use the Newtonian laws. So what you study, maybe you're doing in your class 12 or so, some questions about what is the velocity with which you have to launch to put a satellite in a geosynchronous orbit or something. So all that is fine. It's well described. As I said, Mangalyaan was launched and it followed its trajectory to Mars from the Earth using Newton's laws. There are a few things which you need the Einstein corrections even on Earth now, because our technology has become so sophisticated. Modern GPS systems, maybe many of you know, there's this GPS position system by which you can, through the satellite signals, it tells you where you are. Right nowadays, many of you have smartphones and you can find out on Google Maps exactly where you are. If you want to locate how does it locate? The smartphone sends a signal to a satellite, and there are several satellites, and it triangulates and locates your position. If you need to find your position to something less than a meter, you need to take into account corrections in the time of the signal going to the satellite, which come from Einstein's theory. So modern GPS systems need to take into account the corrections due to general relativity if you want to make them highly accurate. So that's an instance where on Earth also we have where general relativity plays a role. So yeah.
Thank you, sir.
So no further questions. Let's thank Rajesh for...
Okay, so now let's get on with the prize distribution ceremony. First, the level 1 exams for students of classes 9 and 10.